Today we will continue with completely new topic, magnetic field and magnetic forces. This is also a very important topic for many fields of science, and we will talk about magnetism, which is widely used in many areas of daily life. We will talk about properties of magnets and how magnets interact with each other. Let's consider two magnets. So what is the interaction mechanism between the magnets? And we will try to analyze magnetic forces on moving charged particles, negatively charged particles, positively charged particles, and what are the magnetic forces on that charged particles. And during the next lecture, we will also talk about magnetic forces on current carrying conductors. So let's consider that there is a wire and there's a current on that conducting wire. So what are the effects of the magnetic forces on current carrying conductors? We will talk about all these things. We will see the difference between magnetic field lines and electric field lines. We have seen electric field lines during the last lectures, okay? So today we will discuss magnetic field lines. And of course, we will also talk about practical applications of magnetic fields in chemistry, in physics, in biology, including electric motors everywhere. So there are many applications of magnetic fields, magnetic materials. And during the next lecture on Thursday, I hope we will talk about what is the behavior of the current loops when they are placed in a magnetic field. This is the first page of the chapter 27 from Young and Freedman. Here you see a paragraph starts with magnetism, and here I have magnified that paragraph from the Young and Freedman. What do you see here? This information is very important to motivate you. Magnetic phenomena were first observed at least 2,500 years ago in fragments of magnetized iron ore, demir cevheri in Turkish, found near the ancient city of Magnesia, now Manisa in western Turkey. These fragments were what are now called permanent magnets. Okay, here in Manisa in Turkey, magnetism phenomena first observed. So this information taken from the Young and Freedman, you can find it there. So there are many permanent magnets, okay? The most familiar examples of magnetism are permanent magnets. So permanent magnets attract unmagnetized iron objects and can also attract or repel other magnets. Here we have a compass needle. A compass needle is also formed from a permanent magnet. It is aligning itself with the Earth's magnetism, okay, which is one of the example of that interaction. So we will talk about this. But the fundamental nature of magnetism is the interaction of moving electric charges. So after that lecture, you will see and you will learn how can magnetic forces, which act only on moving charges, explain the behavior of a compass needle. So you will see all the things within that chapter. So now let's talk about magnetic poles. What is pole? Kutup in Turkish you can say, okay? If a bar-shaped permanent magnet like this one, in Turkish like çubuk, okay, bar-shaped permanent magnet, or bar magnet is free to rotate, one end points north, this end is called a north pole or end pole. Let's consider that this is a bar magnet, okay? And then you suspended that bar magnet with a rope, for example, and it is free to rotate around itself. So if it is free, one end of that bar magnet will always show the north pole of the Earth, okay? So, and the other one will show south pole of the Earth, like the compass needle, okay? This is talking about this. So what you see here, the interaction between the poles. Here we have a magnet bar. This is the N pole. This is the S pole of the magnet bar. Here we have another magnet bar, and this is the S pole and N pole. So this N pole apply force on this. This S pole applies force on this N pole, okay? And the force between the poles is attractive. You can consider that positively charged particle and negatively charged particle, and there is an attractive electrostatic force in between. You can consider like this, but it is of course completely different. So here we have S pole and N pole, and there is an again attractive force. And the second situation, like poles repel each other. Here we have N pole, they repel each other, okay? Force is repulsive. Again, S pole, repel each other. So this is the interaction mechanism between magnetic poles. So we have two types of behavior, attractive forces and repulsive forces between the poles, magnetic poles. And very important information. So let's consider that here you have a magnet bar and you have another metal object which contains iron, okay? So what will happen in between? An object that contains iron but is not itself magnetized. Let's consider that this is not magnetized at the beginning, but an object that contains iron is attracted by either pole of a permanent magnet. This is very important. Whenever you put that material close to the N pole of the magnet or close to the S pole of the magnet, this material will be attracted by that magnet bar, okay? So we will talk about this. This is the attraction that acts between a magnet and the unmagnetized steel door of a refrigerator. So you can think about this. For example, this is a picture of Istanbul, okay? And on the back side, there is a permanent magnet, okay? So if you put on the door of the refrigerator, it will be attracted, okay? This is magnet and magnetized, but the door of the refrigerator is not magnetized, but there is an attractive force between that permanent magnet and the refrigerator door of the refrigerator. So what is the source of this attractive force? So because the refrigerator door includes some iron or magnetic material, okay? Not only iron, it is important to remind you here that in periodic table, nickel and also cobalt are magnetic materials. Or if you make alloy from iron, cobalt, and nickel, for example, alloy from nickel and cobalt, alloy from iron and cobalt, or alloy from iron and nickel, they will also become a magnetic material, okay? So we will talk about this. So let's continue with the magnetic field of the Earth. Here you see Earth. I will go into detail. First of all, I would like to give you short information. The Earth itself is a magnet. So there is a magnetic field around the Earth. This is for sure, certain. Its geographic pole here, geographic pole, is close to a magnetic south pole. Okay, magnetically, this pole is south pole, And magnetically, this pole is N pole. I will go into detail. The Earth's magnetic axis is not quite parallel to its geographic axis. So what is the geographic axis? Geographic axis is the axis of rotation, okay? Earth, so let's say it has certain axis and it is turning around that axis, okay? This is geographic axis. But magnetic axis is not quite parallel to that axis. I will talk about this. And this deviation between magnetic axis and geographic axis is called as magnetic declination or magnetic variation. And on the surface of the Earth, the magnetic field is not horizontal. Its angle up or down is called magnetic inclination. So let's consider that this is the Earth, okay? And what about the magnetic field on the surface of the Earth? Sometimes it is like this, sometimes it is like this, okay? Sometimes like this. So magnetic field is not horizontal at most points on Earth's surface. So don't forget also that information. This is called as magnetic inclination, magnetic declination, magnetic inclination. So they are talking about different things. So now let's go into detail here. So this is the Earth. You can see that the South America, North America here Europe, here you see Africa, okay? And here you can see Canada, for example, okay? Let's consider like this. And this is the North geographic pole, North Pole, okay? This is the Earth's rotation axis, this red one, okay? Earth's rotation axis. This is South geographic pole or South pole of the Earth, but the magnetic poles are completely different. So let's consider that within the Earth, there is a magnet bar or magnet, okay? But its North Pole is located here and South Pole is located here, completely opposite to the geographic poles. Don't forget this. So what happens if you put a compass here? Compass needle, for example, let's consider that this is a compass, okay? Pusula in Turkish. So this is the red one is the North Pole of the compass. This is the South Pole. So since there is an attractive force between North and South in terms of magnetism, so this will show the that point. This is the actually geographic North Pole, okay? So we have magnetic field lines from north to south magnetic poles around the Earth. So let me read that information, then a little bit go into detail. The field which is caused by currents in the Earth's molten core. So what is the source of magnetic field of the Earth? Currents in the Earth's molten core changes with time. Geologic evidence show that it reverses the direction entirely at irregular intervals of 10⁴ to 10⁶ years. So what is the meaning of that? The magnetic poles of the Earth changes and completely reverses at irregular intervals. For example, 10,000 years, okay? After 10,000 years, the compass will show that part of the Earth, okay? So this is also very important information. And I have already told that the geomagnetic North Pole is actually a magnetic South Pole. This is geographically North Pole, but magnetically a South Pole. It attracts the end pole of a compass. Magnetic field lines show the direction a compass will point at a given location. So if you put compass in different points on Earth, so compass will be aligned along the magnetic field lines like this. The Earth's magnetic field has a shape similar to the produced by a simple bar magnet. although actually it is caused by electric currents in the core. The Earth's magnetic axis is offset from its geographic axis. So what we see here, that this is the geographic axis and this is magnetic axis. So there is some angle in between. Do you have any question here? Okay, then let me continue. So let's talk about magnetic monopoles. So in electricity, we have talked about electric poles, electric dipoles, right? So the situation is completely different in magnetism. Magnetic poles always come in pairs, okay? Always N and S poles are together. There is no experimental evidence for magnetic monopoles. For example, in electricity, you can completely charge a metallic sphere with only positive charges or only with negative charges, okay? In magnetism, you cannot get only N pole or only S pole, okay? Let's consider that you are breaking this magnet into two parts. Whenever you break them here like this, suddenly this will be N and S poles, and this part will have N and S poles, okay? This such situation will not happen. Let me draw. So you break them, for example, into two parts like this. So it will not be like this. This is N pole, this is S pole. It will not be like this, okay? This will never happen in magnetism, okay? You will only get that situation. N pole and S poles will be present together, okay, in the naive parts again. So this is the main difference between electricity and magnetism. There is no magnetic monopole. Okay, now let's consider the behavior between electric currents and magnets. So here we have a compass, okay? So it is showing North Pole. This part of the compass needle is showing North Pole. This part is showing S pole. We have a wire here, conducting wire around the compass. Maybe I should write it like this. So here we have a wire, okay, a conducting metal wire, let's consider, and the current is 0. There is no current, and here I have a compass. And I am taking that compass on top of that wire, okay? So this is what we have done here on the left side. So now let me continue. So if there is no current, this compass will not be affected, okay? It will continue to show the North Pole. But whenever you derive current through the conducting wire, so now we have current in the wire, so this current will produce magnetic field lines around the wire, okay? So in addition to the Earth's magnetic field, you will have magnetic fields produced by that wire. Then the compass needle will be deflected, okay? So this is discovered by Hans Christian Ørsted in 1820. I think he was a Danish physicist, scientist. So he invented that electric current, if an electric current runs through the wire, the compass needle deflects somewhat. This was very important investigation and very important discovery in physics, in science. So after that discovery, we started to produce electromagnets. So until that discovery, for many thousand years, 2,500 years, we have just used only permanent magnets. But after that discovery, we have started to use also electromagnets by applying current through the conductors. We started to produce such magnetic field sources. So we will talk about this during the next chapter. So now let's try to understand the nature of the magnetic field. So what is the magnetic field and how it behaves? We will talk about this. A moving charge. So what is the moving charge? Moving charge is the current, right? So current is the movement of the charges from one place to another place. A moving charge or current creates a magnetic field in the surrounding space, like here. If you drive current through the conductor, it will produce magnetic field lines around itself, okay? So the magnetic field exerts a force on any other moving charge that is present in the field. So we will talk about this one, but what about the magnet bar? Why this magnet bar, this permanent magnet, is affected by the current and affected by the magnetic field produced by that current? We will also talk about this one during the next chapter. So like an electric field, a magnetic field is a vector field, okay? It has certain direction like electric field. That is a vector quantity associated with each point in space. So for the representation of the magnetic field, we will use symbol B, okay? Capital B, which is vector. This is showing us magnetic field. But in some books and publications, H is also used instead of B. But within the Young and Freedman University physics, we only use B in order to define the magnetic field. Actually, there is a small difference between B and H, but I will not go into detail. Otherwise, you will mix it. Okay, it is not necessary. So just consider that we will use B for the magnetic field. So here, what you see, here we have a magnet bar. Look at that one. This is the N pole of the magnet bar. This is the S pole of the magnet bar. So what about the direction of the B? The direction of the B is defined by the magnetic field lines. And we have magnetic field lines from N pole to S pole. Okay, from N to S. Don't forget this one. So we will also give a detailed information about this. Here, I would like to show you a bio application, spiny lobsters or Caribbean spiny lobster. So what is this? As much as I remember, Turkish name is dikenli istakoz. Caribbean spiny lobster, this is Latin name, Panurlirus argus, has a relatively simple nervous system. It is remarkably sensitive to magnetic fields. So their nervous system can detect magnetic fields. It has an internal magnetic compass that allows it to distinguish north, east, south, and west. This spiny lobster can determine north, east, south, and west, okay, by using its internal magnetic compass. So because this creature can detect magnetic field, this lobster can also sense small differences in Earth's magnetic field from one location to another. So Earth's magnetic field changes. Maybe we will also talk about this. So around the poles, magnetic field, Earth's magnetic field increases, and here around the equator, Earth's magnetic field goes down, okay? So depending on the altitude from the Earth's magnetic field also changes, okay? So from one position to another position on Earth, magnetic field changes. So this lobster can detect that small differences in the Earth's magnetic field from one location to another and may use these differences to help it navigate. So this is very nice bio application. Now let's talk about the magnetic force on a moving charge. The magnitude of the magnetic force on a moving particle is proportional to the component of the particle's velocity perpendicular to the field. So what we mean with that information, I will explain here. So here we have magnetic fields shown by B, homogeneous uniform magnetic field, let's consider. And here we have a positively charged particle. The charge is Q, and it has certain velocity along the magnetic field. So what about the force due to the magnetic field on that charged particle? The force is zero, because a charge moving parallel to a magnetic field experiences zero magnetic force. We will explain why. It comes from the force formula in case of magnetic fields. So the magnetic force is best represented as a vector product, like this. The force due to the magnetic field is given by that expression. This is the charge of the particle. This is the direction of the magnetic field. This is the velocity of the particle. In the previous case, the velocity is parallel to the magnetic field in that direction or in that direction, or parallel to the magnetic field. So when the velocity is parallel to the magnetic field, the force will be zero, because here we have a vector product between velocity and magnetic field. Okay, so only if they are perpendicular to each other, or if only velocity has a perpendicular component compared to the B, then we can see a magnetic force acting on a moving charged particle. Okay, any question here? So we will also talk about the sign of the, direction of the force, but let me discuss this one during the next transparencies. A charge moving at an angle phi. So in the previous case, the angle between velocity of the charge and the direction of the magnetic field was 90 degrees, completely perpendicular to the magnetic field, okay? The particle is moving. But what about if the particle is moving with some certain phi angle compared to the magnetic field? This is the velocity, particle is moving like this, and then this is the direction of the magnetic field. So as I told you during the previous transparencies, if the velocity has perpendicular component, so this velocity has two components. One is this one, the other one is this one, okay? If you draw the vector components of that velocity, we have one component here, another component here. So due to that component, there will be no magnetic force, because velocity and magnetic field are parallel to each other here for that component. But here we have a perpendicular component of the velocity. So due to that perpendicular component, we will have a force. So what about the perpendicular component of the velocity? We can write it like this: v times sinus phi. V times sinus phi will give us that perpendicular component. Then the force can be written like this. And what about the direction of the force? Here we have drawn like this, but how to get this one? Direction of the force is given by right-hand rule, okay? So how to do that? Let's consider we have a positive charge. This is the direction of the magnetic field. This is the direction of the velocity. The charge is moving like this in that direction. So what is the magnetic force due to the magnetic field? First of all, we place the V and B vectors tail to tail. This is the tail of the B vector. This is tail of the V vector. And imagine turning V toward B in the VB plane, here in that plane, okay? You turn your fingers from V to B, okay, by applying right-hand rule, and your thumb here will show the direction of the force. Again here, okay, this is the direction of the velocity, this is the direction of the magnetic field, and use that fingers showing the direction of the velocity, and then curl them to the direction of the magnetic field, and then this thumb will show us the direction of the force, okay? This is for positive charges. But if you have negative charge, then the direction of the force will be opposite, okay? Here we have direction of the force, same condition, but the charge is negative, then the direction of the force is opposite. Same condition, direction of the B, direction of the velocity, but the charge is positive here, direction of the force is this one. But if you have negative charge, then the force will be opposite. So this is the right-hand rule for magnetic force. You have already learned that right-hand rule during the Physics 1 lectures. So here we have two charges. One is positive charge, the other one is negative charge. And we have homogeneous magnetic field shown by blue color, okay? And these two charges are moving in same direction. This is the velocity of that charge. This is the velocity of that charge. So they are moving together. Whenever they enter into that magnetic field, this one will feel magnetic force in that direction by the right-hand rule, okay? This one will feel opposite direction by the right-hand rule. So the magnetic forces on the charges are equal in magnitude, but opposite in direction. Any question in that part? Let me continue. So the units of magnetic field, let's talk about this. Here you see force, here you see Q, here you see velocity, and here you see magnetic field. And I would like to calculate the unit of the magnetic field. So if you take B from that equation, you will get that expression, F over Q times V, right? So what was the unit of F in SI? Newton, right? What is the unit of charge? Coulomb, put it there. What is the unit of velocity in SI? Meter per second, right? So put them here. So what we have here, Coulomb per second, and we know that Coulomb per second is given by 1 amp, and put it there. Then finally, unit of magnetic field will be given with that expression, 1 Newton per ampere times meter. Okay, this is the unit of the magnetic field, but it is also called as Tesla, okay, in honor of Nikola Tesla. So 1 Tesla is given by 1 Newton per ampere times meter. Another unit of magnetic field is Gauss, okay, which is also used. You know Gauss' name from the Gauss law, okay? So 1 Gauss is equal to 10 to minus 4 Tesla, which is also widely used. Let's compare the magnetic fields of different sources. The magnetic field of the Earth is of the order of 10 to minus 4 Tesla, or around 5 Gauss. For example, in Gebze, it is around 0.35 Gauss. We have measured it at Gebze Technical University. But from the Ecuador or from Turkey, if you go to the north, to the Russia, for example, this Earth's magnetic field will increase. So we have already discussed this one. And what about the magnetic fields of the atoms, also magnetic fields of the materials within the interior of the atoms? So if you consider, for example, iron, let's consider this is made from iron, and the magnetic atoms of the irons are connected to each other with a molecular field or exchange interaction. Okay, this is detailed information about magnetism, but I will try to give you an idea to compare the magnetic field sources. So the molecular field is around 10 to 3 Tesla, okay? Not 1 Tesla, 10 to 3 Tesla. Huge magnetic field is present within the magnetic materials. But in the world, the largest steady magnetic field can be produced at present in the laboratory is about 45 Tesla. Okay, much smaller than the magnetic field present within the iron. Okay, within the iron it is 10 to 3 Tesla, but we can produce 45 Tesla in the laboratory. And some pulsed current electromagnets can produce fields of the order of 120 Tesla for millisecond time intervals. So this is just comparison of the magnitude of the magnetic fields for different sources. So now let's see applications of this magnetic fields. This is cathode ray tube. So what is cathode ray tube? We have used it in the old televisions. Okay, maybe you remember that type of cathode ray tubes. In Turkish we say tüplü televizyon. Okay, older types of the televisions. Here what we have, the electron beam in a cathode ray tube, such as that in an older television set, shoots out a narrow beam of electrons. Here we have an electron beam source or electron source. Okay, and if there is no magnetic field, let's consider that the magnetic field is 0. This electron beam goes along the green direction. Okay, this is the velocity of electrons, and let's consider that they are traveling along the x-axis without any deflection. Okay, but whenever you introduce magnetic field, so since they are negatively charged, there will be a force along the z direction. This is x, this is y, this is z. Velocity is along the x direction, b is along the y direction. Then we have magnetic force due to the magnetic field along the z direction. And what you see here, electron beam, electrons will be deflected, okay, on the screen. So this is the working principle of cathode ray tubes. So what about the magnetic fields of the body? In the previous chapters, I have given many biological examples. Okay, we have discussed the cells, and we have discussed the membranes of the cells. We have discussed that there are charged particles within the cells, okay, especially in nerve cells. And we have discussed the working principle of the nerve cells. So what about the magnetic fields of the body? Do we have any magnetic field within our body? Yes, we have magnetic fields. They are very small, but we have them. So all living cells are electrically active, we have already discussed, and the feeble electric currents within your body produce weak but measurable magnetic fields. If you have electric current, then it means that you have magnetic field, okay? If an electric current present within the system, it means that you have magnetic field. So for this reason, our body produces weak but measurable magnetic fields. The fields produced by skeletal muscles have magnitude less than 10 to minus 10 Tesla, and our brain produces magnetic fields that are far weaker, only about 10 to minus 12 Tesla. So there are many efforts to measure such small magnetic fields by using magnetic field sensors. Okay, this is very active research area in physics, also in material science. So now let's try to solve the questions. Here we have first example, magnetic force on a proton. Here we have a beam of protons. What is the beam? Beam in Turkish demet. It means that we have many protons. Okay, they are collected together. This is the beam. A beam of protons. Proton has that charge. It moves at 3 times 10 to 5 meter per second through a uniform 2 Tesla magnetic field directed along the positive z-axis. This is the x-axis, this is the y-axis, and here we have the z-axis. So this is the proton beam, positively charged, and this is the velocity of the proton beam. This is the magnetic field along the z-axis. The velocity of each proton lies in the xz plane. This is the xz plane, and proton beam is going in that direction, in xz plane. And it is directed at 30 degrees to the positive z-axis. So you can see that, okay, 30 degrees between V and B. Find the force on a proton. So what is the force due to the magnetic field acting on the proton or proton beam? So we will use that expression. Force is given by that expression. So here we have equation QVB sinus phi. This is the charge of the proton. This is the velocity of the proton. They are given. This is the magnitude of the magnetic field, which is uniform. It is also given 2 Tesla. And the sinus of the angle between them, it is also given. Put them here. Then we have 4.8 times 10 to minus 14 Newton. Okay. So then let's talk about magnetic field lines. We can represent any magnetic field by magnetic field lines. Here we have a magnet bar. This is the N pole of the magnet bar. This is the S pole of the magnet bar. And we have magnetic field lines from N pole to S pole. Okay. So this field lines also present within the material, okay? They are a complete loop. You can consider like this. They start from, they leave from the N pole and they enter into the S pole. Always like this. We draw the lines so that the line through any point is tangent to the magnetic field vector at that point. So look at that one. If you draw a tangent here, at each point, the field line, magnetic field line, is tangent to the magnetic field vector B. So here we have magnetic field line, and this is the magnetic field vector. And these field lines never intersect. We have already discussed this one in electric field. So the more dense the field lines are packed, the stronger the field is at that point. So look at that one. So here around the poles, we have more field lines. Then the magnetic field is stronger around the magnetic poles. This is also the case for the Earth's magnetic field. If you go to the poles, to the North Pole or South Pole of the Earth, the magnitude of the magnetic field will increase since we have more densely field lines. Magnetic field lines are not lines of force. This is important, very important. Don't forget this one. So this is the magnetic field direction, okay? Uniform magnetic field. And this is the velocity of a positively charged particle. And what about the line of force? Line of force is this one, okay? Force, magnetic force due to the magnetic field is perpendicular to the magnetic field lines, okay? So field line is in that direction and force is perpendicular to the magnetic field lines. In electricity, it is completely different. If you consider electric field and the force due to the electric field acting on a charge, they are along the same direction or in the same axis, okay? But here they are perpendicular to each other due to that relation here. So now let's discuss the magnetic field lines produced by some common sources of magnetic field. Here we have a magnetic field of a C-shaped magnet. Like this, you have a magnet, okay, with C shape. So this is the shape of the magnet, okay, with C shape. And we have magnetic field lines like this within the magnet. And here there is nothing, you see, there is an interval because there's a C-shaped magnet here like this. And what are the magnetic field lines in that region? If you magnify it, magnetic field lines are like this. They are more or less homogeneous, just between the magnetic poles. So here we have magnetic field of a straight current carrying wire. We have already discussed this one here. Let me remind you, many transparencies. So this one, okay, we have a wire, conducting wire, and we apply current, okay? So due to that current around that wire, we have magnetic field. So what about the direction of that magnetic field, which is presented here? If you have current like this, just use your right hand, okay? This thumb will show you the direction of the current, and the direction of the fingers, direction of that fingers will show you direction of the magnetic field, okay? So by using right hand rule, this is showing the thumb, and this 4 fingers are showing the direction of the magnetic field. If you have a wire, conducting wire, if you apply current, then a magnetic field will be produced like this. The magnetic field produced by that conducting wire can also be presented like this. What do you see here? The direction of the B changes, okay? So here down here into the plane, now it is going up, and now it is out of plane, okay? So for the B directed out of plane, we are showing this points like here, okay, dots. So this is showing that the direction of the magnetic field is from the screen to us, you can consider. And here we have crosses. The direction of the magnetic field is directed into plane. So you can consider you have an arrow. This is the front side of the arrow, and this is the back side of the arrow. Back side is shown by that symbol, you can consider, okay? So the direction of the magnetic field produced by a straight current carrying wire can be shown also like this. If you have any question in that part, you can ask. And I will continue with the magnetic fields of a current carrying loop. This is a loop. But you see here, you apply current, and current goes like this, okay? This is a loop. You can consider like circle. So what is the magnetic field around that loop? The magnetic field, again, defined by the right-hand rule, okay? This thumb, again, will show the direction of the current, and these fingers will indicate the direction of the magnetic field. So you will use that right-hand rule in order to find the direction of the magnetic field. So we have this type of magnetic field lines, okay? So here like this, and here we have like this. So in the center, you have more or less homogeneous magnetic field. But in order to get homogeneous magnetic field, you have to use solenoids, okay? Current carrying coil. What we have here, we have many turns, okay? We have many turns of the conducting wire. Then you apply current. So again, you are in order to find the direction of the magnetic field here, in that case, what you see here, these arrows will show the direction of that fingers, okay? The current is shown by that fingers, and then this thumb will show you the direction of the magnetic field, like this, okay? So currents are shown by the fingers, and direction of the magnetic field is shown by the thumb in that case, by applying right-hand rule. So here we have current, here we have magnetic field. So if you change the direction of the magnet, if you change the direction of the current within the solenoid, then you can also change the direction of the magnetic field. Now we have magnetic field in that direction. By changing the direction of the current, you can apply magnetic field in that direction. Okay, so now let's give also very short information about magnetic field lines of two permanent magnets. Here we have one permanent magnet, N pole, S pole here, another permanent magnet, S pole, N pole here. And here you see iron particles, iron powder or iron fillings, demir tozları in Turkish, okay? So here you have two magnets, N pole, S pole, another magnet, S pole, N pole, and then iron fillings are oriented like this due to the magnetic field lines produced between N and S poles. So field lines also presented like this, okay, from N to S. This is the direction. So they are leaving from the N and they enter into the S, okay, leaving from N goes to the S. So any question here? If not, let me continue with the magnetic flux. You remember the electric flux, okay? The topic is more or less same. You will easily understand. And if you remember the Gauss law for the electricity, it will be very useful for you to understand the mechanism here. So in order to define the magnetic flux, we can divide any surface into elements of area dA, very small. Here we have, let's say, a surface, and we divide that surface into very small dA areas. And the magnetic flux through the area element is defined with that expression. Remember that we have used phi E for the electric flux, but for the magnetic flux, we use phi B, okay? And d phi B, the flux through the area element, very small area element, okay? Here we have surface. Here we have surface normal, okay? dA, and here we have direction of the magnetic field, and we are looking for the perpendicular component of the magnetic field to the surface, okay? So we need perpendicular component of the magnetic field. So the total magnetic flux through the surface is the sum of contributions from the individual area elements. Then you will integrate. So perpendicular component is given by B times cosine phi. You see, this component is given by B times cosine phi. Take this one, and element of surface area for very small area, and integral from the whole surface of the system, and it gives us magnetic flux through a surface. So you can also write that one, B cosine phi, B perpendicular, component of B perpendicular to surface, or you can write like this one, a scalar product of this one, B times dA, okay, vector element of surface area. But what about the magnetic flux through any closed surface? We have done it for the electric fields, okay? Here we have magnetic field, here we have the area of the closed surface, and this is the closed surface symbol here within the integral, so which is equal to 0 in case of magnetic fields. So remember the electric flux for the closed surface. Remember that formula. Let me draw here. Gauss law. You remember? This was equal to Q enclosed over epsilon 0. We have seen this one in the Gauss law in previous chapters. So if you have, let's consider that if you have a metallic sphere which is positively charged, okay, then the electric flux through that closed surface, if you choose a closed surface like this, the electric flux is given by that expression, Q enclosed. Here we have positive Q over epsilon 0, okay? But let's consider that within that closed surface, we have same amount of minus Q charges. Then the total charge Q enclosed will be 0, right? Then the electric flux, this is given by, okay, phi E, electric flux here will be 0, since the total charge is 0. So you can make an analogy for the magnetic flux here, since we don't have any separate N pole or S pole for the magnets. You cannot get any separate N pole, you cannot get separate S pole. They are always together, like positive charges and negative charges are together, okay? You can consider like this. Since when you have equal amount of positive and negative charges, you will get total charge is 0, okay? So you can consider like this, you can make an analogy. In case of magnetism, we never get separate N pole or S pole. There is no magnetic monopole. For this reason, we always have that condition. For this reason, here we have on the right side, we have 0. So this is the explanation of that magnetic flux through any closed surface. If you have any question in that part, I will try to explain or answer. Okay, after deleting the board, I will continue with unit of the magnetic flux. The SI unit of magnetic flux, phi B, is called the Weber in honor of Wilhelm Weber. 1 Weber is equal to 1 Tesla times meter square. The unit of magnetic field is Tesla. The unit of area is meter square, which is equal to 1 Weber, unit of magnetic flux. Okay, now what about magnetic flux density? Magnetic flux, this is magnetic field, and we have another term, magnetic flux density. The name of this guy, B, is magnetic field, okay? But sometimes it is also called as magnetic flux density. If you take B from that expression, you will get that one, d phi B over dA, okay? For this reason, the magnetic field is sometimes called magnetic flux density. So another name of magnetic field is magnetic flux density. You can see many books and papers with that name, okay? This B also called as magnetic flux density, magnetic field or magnetic flux density. So now let's try to calculate magnetic flux. This is another example from the book, example 27.2. So here we have a figure, okay? A perspective view of a flat surface. This is a flat surface with area 3 square centimeter in a uniform magnetic field. This is the magnetic field. The magnetic flux through this surface is given by 0.9 milliweber. Magnetic flux is given. So this phi B is given. Find the magnitude of the magnetic field and direction of the area vector. So what is given? Area is given, A, okay, and magnetic flux is given. The question is that what is the magnitude of the magnetic field? B is asked, and also direction of the area vector is X. So we need to calculate phi, or we need to know the phi angle between magnetic field and surface. So here we have 30 degrees, which is given. If you put it here, okay, 30 degrees here, this is the surface normal, and this is the direction of the B. So the angle between surface and B is given by 60 degrees. So then by using that expression, take the B instead of flux, put that number here. Instead of milliweber, just use 10 to minus 3 Weber. And then A is given, okay, in square centimeter. We have to use in square meter. Then just use cosine 60 degrees. Then we can find 6 Tesla. So this is the magnetic flux calculation. So now let's talk about motion of charged particles in a magnetic field. We have charged particles and we apply magnetic field. So what about their motions? This topic is very important. I will try to finish that part of the chapter with the examples, okay? Here, we have a positive charge and it has that direction. This is the velocity direction. And here we have magnetic field into the screen, okay, into the paper. You can say when a charged particle moves in a magnetic field, this is the magnetic field, and particle enters into that magnetic field. It is acted on by the magnetic force. So this magnetic force will be applied to that charged particle. We have already discussed. The force is always perpendicular to the velocity. This is velocity, this is force. So it cannot change the speed of particle, only its direction. This part is very important. Just try to understand. So in order to change the speed of the particle, you need a force along that direction, okay? But there is no force acting on the particle in that direction, okay? Or in that direction. The force is always perpendicular to the velocity due to the magnetic field. So if there are no other forces acting on the system, the velocity of the system, the velocity of the particle will be constant, will be same, okay? The speed of the particle will not change, only its direction will change, okay? So don't forget this one. A charge moving at right angles to a uniform B field moves in a circle at constant speed because F and V are always perpendicular to each other. So we will not decrease the speed, we will not increase the speed, we will just change the direction of the speed, okay? Then we will have a circular motion, okay? Particle is coming from this V velocity and enters into the magnetic field. Here we have magnetic field, magnetic area, okay? And this is the direction of the magnetic field into the page, into the screen. And whenever it enters, it moves like this. So now let's apply Newton's second law for a circular motion with constant speed. Remember your information from physics 1. So what was the second law? If the total F, total forces acting on a system, is different from 0, it is given by m times acceleration, mass times acceleration. So in circular motion, we have a centripetal acceleration, which is given by v square over r, right? This is radius of the circle. This is the velocity of the particle. And what about the forces here? We have only one force acting along the radial, right? We have only forces like this. So force is given by here, net force is given by QVB, and this is the mass of the particle, and centripetal acceleration. Instead of A here, put centripetal acceleration. Then by using that expression, this V is cancel one of this one, and then radius of that circle is given by mv over qb, okay? So this formula is very important and very useful. Don't forget this one, okay? Very easy to get that formula. So if the charge q here is negative, the particle moves clockwise, okay? If it is positive charge, it moves counterclockwise, but if it is negative charge, it moves like this, okay? So now what about the angular speed of the particle? The angular speed omega can be found with that formula. Remember that the linear speed is given by radius times angular speed for the constant speeds. from chapter 9, you can remember, okay? So instead of R, just put that formula, okay? Then omega, if you take omega from that expression, V over R, and then angular speed, omega is given by Q times B over M. And by using that expression, you can also calculate frequency, the number of revolutions per unit time. So this is the frequency, how many revolutions are present per unit time, or you can also find the period, okay? So by using that expression. So this frequency F is independent of the radius R of the path. So you cannot see any radius here, okay, within the frequency or this is angular speed. There is no radius. It is called the cyclotron frequency in a particle accelerator called a cyclotron. So these cyclotrons are very important devices, and they are still used to produce radioisotopes for nuclear experiments and also to produce radioisotopes for cancer therapy. So in as much as I remember, in Gebze, one company used that cyclotrons, and also in Ankara, there is one cyclotron to produce radioisotopes. Okay, here we have discussed the motion of charged particles in a magnetic field. We have a charged particle, we have a magnetic field, and then the charged particle entered into the magnetic field with some certain velocity, and then we have force like this, and we have a circular motion. But what about a helical motion for the motion of charged particles in a magnetic field? Here, we have considered that the direction of the velocity is perpendicular to the direction of the magnetic field. And we don't have any other components of the velocity, just perpendicular component to the magnetic field. If there is a parallel component to the magnetic field like this, here we have the Q charge. This is the direction of the velocity of the Q charge, and this velocity has two components according to the magnetic field. Magnetic field is along the x-axis, and this velocity has one component along the x-axis in the same direction of the B, and it has perpendicular component perpendicular to the B direction, okay? What happens in that case? Due to that perpendicular component, there will be a force, okay? Due to perpendicular component, there will be force acting on the charged particle, and due to that force, that particle will have a circular motion, okay? But in addition to that perpendicular component, this particle has velocity in the x direction, positive x direction. So this positive x direction, this will have two motion. One is the displacement along the x-axis due to that velocity, and one is the circular motion due to the perpendicular velocity. So since this has circular motion plus displacement along the x-axis, we will have a helical behavior, okay? The motion of that charged particle will be helical motion. Any question here? But let's consider that we have a non-uniform magnetic field. Here we have a uniform magnetic field. Magnetic field is same everywhere. Direction of the magnetic field is same, and magnitude of the magnetic field is same. Magnetic field is uniform. But what happens if the magnetic field is non-uniform? Here, let me show you by pen. Here I have a coil, and there is a current on the coil. And here we have another coil, and there is a current on the coil on the right side. So due to that coil, this is the direction of the current, which is shown, and the magnetic field lines will be like this. Okay. These are the magnetic field lines. So here we have another coil. This is the direction of the current on the coil. So here we have magnetic field lines. We have already discussed this one. Okay, so between this coil 1 and coil 2, we have such non-uniform magnetic field. You see, magnitude of the magnetic field and the direction of the magnetic field changes between these two coils. So we have non-uniform magnetic field. Then let me continue. Okay, so here we have a non-uniform magnetic field between coil 1 and coil 2, and one charged particle, positively charged particle, enters into that magnetic field, non-uniform magnetic field. So what will happen? This charged particle will have helical motion like this, but this helical motion will also be not uniform, okay, due to non-uniform B here. So this is the direction of B here, direction of the B here, direction of the B here. But the force, the magnetic force acting on that positive charge particle is always into the that region, okay, here along that direction, here along that direction, here along that direction, here along that direction. You can trap that positive charge within that area, okay? Charge particle is trapped within that area. For this reason, this is called as magnetic bottle, okay? You can store, you can trap the charges within that type of magnetic traps. So particles near either end of the region experiences a magnetic force toward the center of the region. Force is always toward the center of the region. So for this reason, you can trap the charge within that magnetic bottle. So what about the application of this one? This is one way of containing an ionized gas that has temperature of the order of 10 to 6 Kelvin. So sometimes, so if you have a plasma, an ionized gas, it has a huge temperature, then you cannot keep that plasma with materials, because it would vaporize any material container. Instead of material container, we use magnetic bottle to keep hot plasmas in a magnetic bottle. So here we have one example. This is an electron beam seen as a white arc here, curving in a magnetic field. Here we have one coil, you see, this is one coil. Here we have another coil. This is the direction of the magnetic field, like this one coil, another coil. And here we have a magnetic bottle, okay, magnetic trap. I mean, you don't see the magnetic trap, but it is there. So then you can keep the charged particles in certain area. And another example is the Van Allen radiation belts. Okay, it is also related to the motion of charged particles in a non-uniform magnetic field. So what we have here, this is the Earth, this is North Pole, this is South Pole, okay? Near the poles, charged particles from these belts can enter the atmosphere. They are coming from the sun, okay? And they produce northern lights and southern lights, also called as aurora borealis, aurora australis, okay? So what we have here, charged particles from sun enter Earth's magnetic field. There's a magnetic field around the Earth, and this magnetic field is not homogeneous, okay? So protons, positively charged particles, trapped in inner radiation belts here, okay? And they have this type of movement. And electrons, negatively charged particles, trapped in outer radiation belts. So we have this type of lights, northern lights or southern lights, or general name is Van Allen radiation belts. So this is very nice example of that motion of charged particle in a non-uniform magnetic field. So now I will continue with another example, electron motion in a magnetron. Maybe first of all, I should talk about what is magnetron. You already know it. You already use that magnetrons in home, okay? So magnetron, a common source of microwave radiation for microwave ovens you have maybe at home, and radar systems, okay? Magnetrons are used. They emit radiation with a frequency equal to the frequency of circular motion of electrons in a vacuum chamber between the poles of a magnet. This is just information. So what is magnetron? So they are used in microwave ovens. And what about the electron motion in a magnetron? A magnetron in a microwave oven emits electromagnetic waves with frequency 2.45 gigahertz or 2450 megahertz. What magnetic field strength is required for electrons to move in circular paths with that frequency? So you would like to keep electrons in circular paths. Okay, frequency is given here. So what is the magnetic field? So we know that formula. Angular speed is given by 2 pi f. Okay, f is given here. Put it there. Instead of hertz, just use 1/second. Okay, and then you get the angular frequency. And in order to calculate B, remember that formula. You see, angular speed is given by Q times B over M. And if you take B, M times omega over Q, M is the mass of the electron, because we are talking about electron motion in a magnetron, and Q is the charge of the electron. We know them, and we have already calculated angular speed. Put it there. Then the magnetic field is required 0.08 Tesla. Okay, so just remember that formula for the circular motion of a charged particle in a magnetic field. We have another example here, helical particle motion in a magnetic field, okay? Example for that type of movement. So let me continue. If you cannot read the letters, let me magnify it, okay? In a situation like that shown in figure 2718, this figure, like helical motion, okay? So the charged particle is a proton, positively charged, charge is given, and then mass is given, and the uniform 0.5 Tesla magnetic field is directed along the x-axis, like this one. Magnetic field is given along the x-axis. But at time t0, the proton has velocity components along the x direction and z direction. Proton has velocity along the x direction and z direction. Y direction, it has no velocity, okay? So you know that since the x velocity and magnetic field are parallel to each other, there will be no magnetic force. But since the z velocity of the proton and the magnetic field are perpendicular to each other, there will be a circular motion. Circular motion plus x velocity along that direction, we will have a helical motion, okay? This is the question. So now let's have a look. Only the magnetic force acts on the proton. There are no other forces. So now at time is at 0, find the force on the proton and its acceleration. We will find the force and acceleration. And B is to find the radius of the resulting helical path, the angular speed of the proton, omega, and the pitch of the helix, the distance traveled along the helix per revolution. So now let's have a look. This is the equation. F is equal to QVB. So here we have a vector product. So what we know that B, where is B? Magnetic field is directed along the x-axis, only along that direction. But V has two components. One is along the x-axis and the other one is along the z-axis. Okay, so then I can write B like this: B times I, only component along the x-axis, and V has component along the x-axis and component along the z-axis. So then put them here in that equation. So this component and this component will give 0. Okay, there will be no magnetic force along that direction due to this vectorial product. And this force will be given by that expression. So just take this Q, put it there. Just take VZ, put it there. Just take B, 0.5 Tesla, put it there. Then we can calculate force in Newton. Okay. So what is another question? It's acceleration. F is given m times a, okay, and F is calculated. M of the proton is given here. Then acceleration is given by 9.58 times 10 to 12 meter per square second. And what is the second question? Find the radius of the resulting helical path. So there is a radius here. Radius in the previous transparencies we have found m times v over qb. The radius is defined by the z velocity of the proton. M is known, velocity is known, q is known, b is calculated. Then the radius is 4.18 millimeter. And another question is angular speed of the proton, which is also given by that expression. We have done it in previous transparencies. Q times b over m. Q is known, b is known, m is known, then 4.79 times 10 to 7 radian per second. We can find the period with that expression, 2 pi over omega. Then the period is 1.31 times 10 to minus 7 second. So what is period? What is the time for just for one revolution? So what is another question? The pitch of the helix, the distance traveled along the helix axis per revolution. So here I have one revolution. Here I have another revolution, and during that revolution, during each revolution, the particle moves along that direction. So the question is that the distance traveled along the x-axis in this period time, then the distance x is given by Vx times period. Vx is given here, put it there. Period we have calculated, put it there. Then the movement along the x-axis just for one revolution is 19.7 millimeter. Do you have any question here in that part? Okay, now I have 3 examples and 4 transparencies, and then I will finish my lecture. So we are talking about motion of charged particles in a magnetic field. Okay, so here I will give you some very useful applications of magnetic fields and magnetic forces acting on charged particles. Here we have a velocity selector. You choose velocities. velocity selector uses perpendicular electric and magnetic fields to select particles of a specified speed from a beam. So let me explain first of all what is the shape, and then I will go into detail. Here we have a source of charged particles. Let's say you produce here positively charged ions, okay? And they have some certain velocity. Let's consider that we have nothing here, no electric field, no magnetic field, and this positively charged particle will continue with some certain velocity along a straight line, right, without any deflection, if the E and B are the zero. So now let's consider that you apply an electric field from positive to negative electric field in that direction. So whenever that Q charge enters into that electric field, it will be deflected like this. Okay, it will be deflected like this because there's an electric field from positive to negative. So there will be electric force in that direction, which is given by Q times E. And if you apply magnetic field into the screen, okay, in that direction, then we will have another force. This is the direction of the velocity. Direction of the magnetic field is perpendicular to the velocity. Then the force will be like this due to the magnetic field. This is the force due to the magnetic field, which is given by Q times V. So here we have two forces when that Q charge is moving. One is electric field force, the other one is magnetic field force. So if they are equal to each other, we have one force here, another force here in that direction. So if they are equal to each other, the net force acting on a system is zero, then it can continue along that direction. Okay? So let's consider that this FE and FB are equal to each other. Q cancels that Q, okay? Then V, velocity, is equal to E over B if they are equal to each other. So only particles having speed, velocity is equal to E over B pass through undeflected, okay? So if we have particles with that velocity, they can go through the straight line without deflection. This is velocity selector. If we have other particles with different velocities, they will be deflected like this. Okay, so but velocities with that condition can go through in that direction without any deflection. Any question here for the velocity selector? Okay, now let's continue with Thomson's E over M experiment. This is another example, very easy to understand. The mechanism is same, okay? So just try to concentrate. Thomson's experiment measured the ratio E over M for the electron in 1897 at the Cavendish Laboratory in Cambridge in England, okay? So E is the charge of the electron, mass is the mass of the electron, and with that experiment, Thomson get that result. So this is the apparatus used by the Thomson. Here we have a cathode, negatively charged. This is EMF here, okay, negatively charged cathode. And here we have positively charged anodes. And electrons are accelerated from negatively charged cathode to the anodes, okay? Here we have slits, very small slits. And then you produce an electron beam, okay? Here we have magnet, another magnet, and you can produce magnetic field in that direction. And here we have two plates. You can produce electric field here. This is positively charged. This is negatively charged plate. Then you can produce electric field in that direction. So if the magnetic field and electric field are zero at the beginning, the electron beam will not be deflected. It will hit the center of the screen, okay? whenever you apply electric field, the electrons will be deflected like this, okay? Since they are electrons, the force is opposite to the electric field. Whenever you apply electric field, the electrons will be deflected like this. They cannot follow that path. But if you apply magnetic field, since the magnetic field will apply a magnetic force in that direction on the negative charges, then you can deflect them like this, okay? If the magnetic force is huge compared to the electric force, they can be deflected like this. If they are equal to each other, then there will be no deflection, okay? So this was the idea behind the Thomson's EM experiment, E over M experiment. So here we have accelerated electrons by applying some voltage, right? And then electron will have some certain velocity due to the acceleration between cathode and anode, right? So the electric potential energy provided by the battery here, or voltage source here, or EMF source here, is given by E times V. This is the charge of the electron. This is the potential difference between cathode and anode. And then this electric potential is converted to the kinetic energy of the electron, mass of electron, velocity of electron. Electron is accelerated. So electric potential energy is converted to the kinetic energy. So from that expression, take velocity of the electron, you will get 2E potential difference over M, okay? So the electron passed between the plates P and P prime, P prime, here we have electric field, and strike the screen at the end of the tube, which is coated with a material that fluoresces at the point of impact. The electrons pass straight through the plates when this condition is specified, as we have discussed here, okay? If the electric field force and if the magnetic field force are equal to each other, we will have that condition. Then the electron beam will go to the center of the screen without any deflection. So then in that condition, this V, instead of V, just use that one, E over B. E over B is equal to that velocity here. Then take E over M from that expression, E over M here. Take this one, E square, electric field between the plates. I know it. Magnetic field between the poles, I know it. And potential difference between cathode and anode, I know it. Then I can calculate E over M, okay? This is what Thomson did in his experiment. So this is my last example of the velocity selector, which is used in mass spectrometers. And then I will give you 2 examples and I will finish my lecture. So let's talk about mass spectrometer. So you select masses, okay, or you count masses. So I can consider like this. Here we see a mass spectrometer used by the Bainbridge, a scientist. So this is the design of the mass spectrometer. It uses a velocity selector to produce particles with uniform speed V, like this one, which we have explained here, but the mechanism is a little bit different. I will go into detail. So here we have a source of charge, positive charges are produced here, and they are traveling with some certain velocity V. And here we have positively charged plate, negatively charged plate, and here we have electric field in that direction. And we have magnetic field from screen to us, okay? Points here are showing the direction of the magnetic field. So since we have positively charged particle here, we have electric force in that direction, magnetic in opposite direction, okay? So if the electric force and magnetic force are equal to each other, this charged particle will go through that straight line without any deflection, right? Good. But here we have another region which was absent here, okay? Here we have no electric field, but we only have magnetic field. So due to the magnetic field, there will be a magnetic force in that direction when particles goes out from that velocity selector. So depending on their mass, they will be deflected with some certain radius, okay? And then they hit on the particle detector here. Here we have a detector. So they will be deflected like this. Since they are positively charged, they will be deflected with some certain radius due to the magnetic field. So this radius here is given by mass of the particle, velocity of the particle, charge of the particle, magnetic field. So magnetic field is constant for all particles here. And charge, let's consider that they have same charge. This is also constant. Let's consider that they have same velocity. And only we have different masses. For example, if you are using that device to separate radioisotopes of the atoms, okay? So they have different masses. So you can separate them because the radius changes. If the mass changes, radius changes. So, okay, if you have small masses, then you will have small radius. If you have bigger masses, then we will have bigger radius. So then you can use that type of devices as a mass spectrometer. So here now I have two experiments, and then we finish our lecture. So this is an E/m demonstration experiment. Again, Thomson experiment. The mechanism is same. You set out to reproduce Thomson's E/m experiment with an accelerating potential of 150 volt. We will apply 150 volt here between cathode and anode, okay? And a deflecting electric field of magnitude 6 times 10 to 6 Newton per coulomb electric field here between the plates. How fast do the electrons move? Velocity of the electrons is asked. And what magnetic field magnitude will yield zero beam deflection? So if you apply electric field in that direction, electrons will be deflected like this. In order to keep them in a straight line, you have to apply magnetic field. So what is that magnetic field? Question B. And with this magnetic field, how will the electron beam behave if you increase the accelerating potential above 150 volt? So at the beginning, we have applied 150 volt. If you increase the voltage here, so what will happen? So first question, what is the velocity of electrons? Velocity is given by that expression. Okay, we have already done it here. 2 times E times potential difference over m, and E is a charge of electron, m is the let's say mass of the electron. Put them here, and then voltage is 150 volt between cathode and anode, which is also given. Then you can calculate velocity of the electron, 7.27 times 10 to 6 meter per second. You can also write this one in terms of velocity of light, lower than the velocity of light. So what is the field to keep them, these electrons in a straight line, okay? You have to apply, we have applied electric field in that direction, and you need magnetic field. So what is the magnitude of magnetic field? In order to keep them, we should have that condition we have already discussed. V must be equal to E over B. Then from that expression, we know the electric field, which is given. We know the velocity we have already calculated. Then you can calculate the magnetic field required. Last question, with this magnetic field, how will the electron beam behave if you increase the accelerating potential? If you increase the accelerating potential, the field due to the magnetic force will be increased due to that expression, okay? If you increase the potential difference here, if you increase the potential difference, kinetic energy, thus the velocity of the electron beam will be increased, then magnetic force will be increased, okay? Then it will overcome the electric force, then this electron beam will be deflected like this. This is given in that question. So this is the last question. Very important application, talks about finding leaks in a vacuum system. Maybe the topic looks like very far from you, but the mechanism is very simple. Let me draw here. Let's consider that here you have a vacuum chamber, okay? And there is a leak here. So air can enter into the chamber, okay? But you don't want it and you would like to check it. So you can use a leak detector here. Let's consider that this is a leak detector. A leak detector contains a mass spectrometer. So we will talk about this. So you are designing a leak detector that uses a mass spectrometer to detect helium plus ions, positively charged helium ions. And charge is given here, mass is given here. Ions emerge from the velocity selector with a speed of 1 × 10⁵ meter per second. The speed of the helium ions here, which is given. Charge is given, mass is given. They are curved in a semicircular path. So they go on a straight line in that direction because electric force due to the electric field and magnetic force due to the magnetic field are equal to in that region. And here they are deflected, okay? So they have semicircular paths by a magnetic field B. And here we have a particle detector. So they are detected at a distance of 0.16 centimeter from the slit here. So this is the distance. Actually, this distance is given by 2r, okay, diameter of the semicircular path. So then calculate the magnitude of the magnetic field. So what is the magnetic field? So we have that formula for the radius. We have already done m times v over q times b. B is asked, m is known, v is known, q is known. Radius is the half of this one, diameter is given, distance, and take the half of it, put it there, you can calculate required magnetic field. So with that one, I finish my lecture. If you have any question, I can try to answer. If not, see you on Thursday. Take care of yourself. Bye-bye.